you look at the single cell in the cortex, only 5% of its connections come to the thalamus and bring data, and everything else is from either local or global or remote cell, but still in the cortex. So, in other words, it's a little, I could make this more technical for the neuroscience inspired people in the room, but it's a little as if the normal state of the brain is something like dreaming, and from time to time you constrain it very, very sparsely with reality, right? But if you have this huge dynamic system, and its behavior changes completely based on only 5% of the connection, or 5% square of the connection. And its behavior changes all the time. So it's also as if, you know, its job was to dream, and by constraining it very sparsely, you have it deal with reality. So now it doesn't work anymore. Maybe it does. No. Maybe, okay. So the other thing is that the brain is doing all these things, including fast real-time motion, like basketball players or so, with components which are 10 million times slower than a transistor, right? Neurons react at 10 to 100 milliseconds, right? And also there are significant delays in transmission. And yet, you know, you get great basketball players who do much, much better than any robot we've ever built so far. Okay. So just to give you a background of a few numbers. Okay. So we'll talk about a few techniques to try and understand all of these things. Okay, one is you're very familiar with, so we'll go very quickly through that Lyapunov analysis and contraction analysis. And then we'll talk about, you know, what this says about gradient descent, and particularly the topology of global equilibria. We'll talk about adaptive control and prediction and model discovery, and we'll talk about transfer learning. And so the first two are tools about stability. And if you think of it, stability is a requirement for something to exist. You know, if something is not stable, actually, you can't even talk about it. But as we will see, these kind of tools can also apply not just to controlling airplanes or robots, but they can apply to understanding the forward dynamics of neural ODEs, or the backward dynamics of gradient learning, or combinations there. Both of these tools, Lyapunov analysis and contraction analysis, are based in different ways on virtual physics. The notion of virtual physics, as we shall see, and as you may be familiar with. Okay. This, and we'll see. Well, okay. This part will show that most elementary results on gradient descent, which are typically based on convexity, can be replaced by much more, actually, strictly speaking, infinitely more general results based on contraction. Okay, so that's what we'll see. We'll talk about adaptive prediction and control and so on. And when we talk about stable, concurrent learning and control of dynamical systems, that's not the field of neural networks. It's fine, but it's not AI. It's what's called adaptive nonlinear control. Okay, and it has been done for a long time. Okay, and that's so that's what we'll talk about. And so we'll see that. And this notion of adaptation is very important because, for instance, it's the basis of all the control system in the Amazon warehouse. Is adaptive nonlinear control. Why? Because you're trying to get high performance. You don't want just to be robust. Okay, if you having robots which move objects which are large and have varying mass properties, you don't want just to be robust. You want to be extremely precise, and that will be the role of adaptive control. And so then we'll talk, and we'll see that in the process we can gain almost a free model discovery. In other words, we can also pick up the right model. And then we'll talk about transfer learning in the context of these tools. The idea being, you may have used batteries of robots for months, or you may have used, days of high performance computing, and you have a nominal thing that a humanoid robot can do. But now you're changing a little the mass properties, you're adding a glove, or you're putting a backpack and so on. And now what do? You don't want to retrain, and you don't want to train on just this variety of settings, because again, you'll get robust but not precise enough. Okay, so you want to recover the properties of the nominal system, which you've worked so hard to achieve through extensive machine learning and so on, when you start changing parameters in the structured way. Okay, and that's the form of transfer learning we'll talk about. In thinking about all of this, recall that control theory, AI, information theory, computational neuroscience, and robotics all have a common origin, which is what used to be called cybernetics. And cybernetics is fundamentally based on the dynamical systems view. Okay? So from that point of view, we're very much in that line. Okay, so let's talk a little about Lyapunov analysis very briefly. You're all familiar with that. I was saying it's virtual physics because conceptually it's an abstraction of energy conservation, right? You're picking a scalar and you have the scalar decrease, and out of that you're showing things, okay? Mathematically, it's a consequence of basic analysis, actually very mundanely, to the fact that if you have a lower bounded scalar function, which can only decrease, it has to tend to a finite limit. Most Lyapunov theorems are based on that simple fact. Okay, but conceptually, it's one of the most beautiful ideas, I think, in the history of science, right? The notion of virtual physics, right? The notion of having a dynamical system and exhibiting a scalar function that decreases like energy, but it doesn't have to be energy. So people keep rediscovering this in a variety of ways. So for instance, the Polyak-Lodakiewicz condition, abbreviated as PL for obvious reasons, is very fashionable these days. Okay, and so it says consider gradient descent. If you pick the value of the cost minus the minimum value as a Lyapunov-like function, you may not know the minimum value, but as a Lyapunov-like function, and require that this converges exponentially with rate m, you compute v dot, and you find that it's gradient times x dot, which is equal to that, and you wanted to rate mu, you wanted to converge exponentially with rate mu. This condition can equivalently be written as this: the condition that the gradient be large enough with respect to how far you're from the minimum. Of course, the sufficient condition is simply that it's larger than mu phi of x, and this is the PL condition. Okay, so sometimes it's proven in a very, very complicated way, right? But it's just requiring that the residual cost is exponentially convergent. Okay, no more, no less. All right. So if you have a Lyapunov theory, you can have it for autonomous systems or non-autonomous systems. So for non-autonomous system, you have a scalar function whose derivative is negative and the second derivative is bounded, then the derivative tends to zero. So this should be the result, okay? It's like the derivative tends to zero should be the result you're interested in. So for instance, suppose that you have a dynamical system with a control input and basis functions times unknown parameters. You're going to choose the control input to modify this dynamical system so that you get a nominal well-behaved system, for instance, a contracting system, as we'll discuss later, but basically a system that you like, so that while F you might not like, but the component of U which creates this F0 you like. And then another component of U is going to try and cancel adaptively as best as it can this term YA. So it's going to create the same basis functions that you know times estimates A hat, which are going to try to cancel this adaptively. And it's easy to show that if you pick as a Lyapunov-like function V0, which would be the Lyapunov function that would correspond to this system x dot equal f of f0, so assuming parameters are exactly known, and you add a quadratic term in parameter estimation error, a hat minus a, then you can show that this adaptation law will make the system behave after transient as if you knew the parameters exactly. It doesn't mean you learn the parameters exactly, because that depends on how complicated the task is, but it will always make sure that you learn just enough about the parameters to converge to the same nominal behavior as if you knew the parameters, right? If you have a robot and you ask it to stay there, you do nothing and you stay there. You've learned nothing about the parameters, okay? But if you ask it to do something very, very complicated with a load, so that there's no way to do it unless you know the parameters of everything, then the same algorithm will learn the parameters exactly, right? So it's like James Bond, if you want. It's learning on a need-to-know basis. You learn just enough to get the parameters. You learn just enough to get the task done. Interestingly, this exact same control, this exact same adaptation law, learning law on the parameters, can be also written, this is the same thing, just a different way to write it, as gradient descent, not on V0, but on V0 dot in parameter space, right? So it's gradient descent on the rate of convergence of the nominal V0. And you find again the fact that you have this learning on a need-to-know basis, because it stops learning when the gradient of V dot is 0, which doesn't mean you have the right parameter. It just means you do the task well. So contraction analysis. So Lyapunov is virtual physics, but if you think about it, it's kind of virtual mechanics. You have virtual kinetic energy and all sorts of things. Okay, and contraction analysis is virtual fluids. So we started doing that because with a very brilliant student named Vinnie Lohmiller, and he was very good at everything. In particular, he was very good at fluids. Okay? And so we started wondering whether instead of doing Lyapunov theory based on kind of virtual mechanics, we could do a sort of virtual physics. Okay? And so it turns out that what this leads to is basically Riemann joining forces with Lyapunov. Okay. In the sense that, so you have a system, a nonlinear system. Contraction means that, by definition, any two solutions of this system converge exponentially. You forget initial conditions exponentially, or you push the system and it comes back to whatever it was. The theorem, the main theorem, is that this is true if and only if the Jacobian of the system, df over dx, which is the linearization of the system, is negative definite in some metric, okay, in some Riemannian metric, okay. And so it's saying you can find global properties of the nonlinear system based on linearization, exact global property, but not based on linearization at a point, based on linearization everywhere. If you take a function, I give you its slope everywhere and its value at one point, you know the function, same thing. So it's not linearization at a point, it's linearization everywhere. But because still it's based on linearization, you can use all the matrix algebra you have ever learned to solve these kinds of problems. So without getting into too much of the details, but that's what the formulas look like. Okay, and you have this metric, which is a product of fatal transpose theory. I don't have time to go through this. The style of doing proofs with contraction is different from the usual style. So for instance, if you take a Lorentz attractor, which is clearly not a contraction system, trajectories don't converge to each other, right? Suppose you measure x, and you're very lazy, so you build an observer for the system by just using the measured x and copy the system y and z, right? So this is the observer of that system. Does it work? Yes, because if you look at the Jacobian and the identity metric, you just find this, which is obviously negative definite. So therefore, just by inspection, right, this is the entire proof, by inspection, this observer will globally exponentially converge to this chaotic system using only the measurement of x at a rate which is the minimum of 1 and beta. This is the entire proof of global exponential converge of this observer on this chaotic system. By the way, the observer will be very robust, okay, because it's contracting. So if it's chaotic system plus noise, it will still work very well. So you have no way to get rid of this. Okay, this says aggregation properties. So the point is, if we take now, contraction applies to non-autonomous systems, right? Systems which have x dot equal s of x and t, so they could have inputs. So because it applies to non-autonomous systems, you can start building combinations of contracting systems, play Lego with it. And you can show that you can always play Lego with contracting systems under very, very simple conditions. You progressively build a very large contracting system, which is just a combination of the subsystems. And you know, we were kind of also inspired by the notion of evolution and so on. The fact that, you know, evolution, of course, learns by building, by piling stuff on top of each other, and so does development. And this says, you know, if you have building blocks that work and you connect them using some very simple rules, you're going to progressively create very large systems that work. So I'll skip this bit because I don't have time. The result, which we thought was obvious, but you know, people you thought was wrong, is actually true, and it's very simple. Is that if you have a contracting system which is driven by a periodic vector input, then all trajectories tend towards a state of the same period. All right, which of course you can think of using for robots, central pattern generators, and so on. So this is completely nonlinear system, right? But if you drive it with a periodic input, and all trajectories will tend towards a state of the same period. Skip this also for that same reason. Okay, so let's get back to, I don't have the titles, but that's fine. So let's get back to contraction. Okay, so you have conditional contraction. So you have this metric, which is product of this matrix theta transpose theta. Theta is itself a function of x and t. And you have this condition for the system to contracting, which is that this equation as a solution, m, which is positive definite. Okay. And so a system will be contracting if there exists a positive definite solution to this equation in m, and a is the Jacobian of the system at every point. And from the point of view of Riemannian geometry, if you want, it means that the geodesic distance between any two trajectories, as measured with this metric, is exponentially convergent. So any two trajectories tend towards each other. More precisely, the distance, the Riemannian distance with respect to the metric, decreases exponentially. And you can show more generally a robustness result, right? That if you start having a perturbation here, then instead of having just these two terms, you have this extra term, which drives this exponentially convergent Riemannian distance. Okay. In particular, if you can make the system tend to zero exponentially, the disturbance tend to zero exponentially, which is exactly what you do, asymptotically, which is exactly what you do in adaptive control, then XP will tend towards the perturbed will tend towards the unperturbed. And similarly, actually, if you only require that this disturbance term is L2, that will also be the case. So, which will say that in the adaptation, you're going to be able to start having adaptive systems which are themselves Lego blocks, combinations of Lego blocks, each of which is going to be driven by a local adaptation mechanism. And as long as these local adaptation mechanisms are either give you a vanishing term or an L2 term, you're going to converge to the nominal combination of Lego blocks. So, all right. So let's go fast, but let's talk about gradient descent. Suppose we apply this to gradient descent. Okay. So obvious result, if you have a x dot equal minus gradient of f, if you consider the identity metric and you compute the Jacobian, right, this system will be contracting in the identity metric if and only if the Hessian is strictly negative definite. In other words, if and only if the function is strictly convex. So contraction in an identity metric is just strict convexity of the cost. Okay. However, and you can apply this to natural gradient, but I don't have time to that. Okay. However, this property doesn't have to be with identity metric. So let me first, sorry, I'm skipping slide because of time, but you can combine these results with gradients or natural gradient. And if you have a hierarchy of such contracting systems, then basically you would have something like backprop. And if you have feedback contracting system, you have something like RL or adversarial learning. So now this is all with natural gradient, but it could be with just gradient or with n-equal identity. Suppose that gradient descent or natural gradient descent converge exponentially. Sorry, suppose that this equation, perhaps with just n-equal identity, just normal gradient, is contracting in some metric. Remember we said if it's contracting in the identity metric, it means that the function is convex. But that's a set of measure zero in all the things that tend towards a global minimum. Because if it's contracting in some metric, it will tend towards a global minimum, right? With the identity metric corresponding to the function being convex, right? So in other words, the reflex we have saying, well, it's a gradient, and so it should be better be convex if we want to. It's not better be convex. It should be contracting in some metric. And then it will always tend towards a global minimum. So now, perhaps even more fun, suppose you take a gradient or a natural gradient. Again, this metric here is the natural gradient. It's not the same metric as the contracting system. So assume that the gradient descent or a natural gradient descent is semi-contracting in some metric. In some metric. Okay, not necessarily that metric, but just in some metric. You can show that all trajectories are going to tend towards a global minimum. So what does semi-contracting, by the way, mean? It just means that in this equation, alpha can be zero. Oops, sorry. In this equation, alpha can be zero. In other words, distances with respect to the metric do not increase. They don't have to decrease, but they do not increase. So suppose the system is contracting in some metric, then all trajectories will tend towards a global minimum, which in general will not be unique. And all the global minima will be path connected by global minima. In other words, you have exactly the same topology you find in deep learning. But you have lots of solutions because the system is overparametrized. And all these solutions are path connected by things which are also solutions. And the only thing that you need for this is that the system be semi-contracting, so distances don't increase, in some Riemannian metric. Okay? And a tempting conjecture, I'm not sure if it's true, but the tempting conjecture is that as the dimension increases or the overparametrization increases, this condition becomes easier and easier to satisfy. Because in some metric, the metric, the complexity is over n squared. Okay, so for instance, here we have a system which does natural gradient. It's going to converge to this set of global minima. And interestingly, you can show it because it's contracting in this metric, and this metric is not integrable. In other words, you couldn't get this result from just change of coordinates. You have to get this result from a Riemannian metric. Okay, so let's talk a little about adaptive prediction. So, and it will be exactly the same in adaptive control. One of the points here of that paper was that, whatever you do in adaptive control, you can do in adaptive prediction. But the structure is very much the same of what we saw in the first few slides, right? You have a nominal system, and then you're going to have an update, okay, of that system parameters to make sure that the system converges to what it would have converged to if you knew the parameters. Okay. Now, it turns out that this structure is nice, but you can do much better than that using exactly the same complexity by implementing implicit regularization. Let me say what I mean by that. You may remember the Feynman lectures on physics, and you know, in volume 2, 12, chapter 12, section 7, it talks about the underlying unity of nature. Feynman wonders, you know, how is it that, you know, in magnetism and in fluids and so on, you only get things like gradients, divergences, curls, and nothing else. Okay. And the answer, he doesn't say it that way, but the answer is that these should all be tensor quantities. They should all be things which are coordinate free. You know, basically that, you know, that the transform in very specific ways so that they are physical objects. And that considerably limits the kind of equations you can have. It doesn't considerably limit, but it doesn't necessarily give you right away all the equations. So what we're saying is, suppose that you have a set of possible physics, a set of possible equations, and you're not sure which one. For instance, you have a potential, but you're not sure if it's 1 over r or 1 over r square or something like that. And similarly, other things like that. What can you do? Well, you can use what we call implicit regularization. In other words, if you, instead of this, remember in the Lyapunov light function, whether in adaptive control prediction, we had a term which was the error term, the task error term. And then we had a quadratic term, alpha hat minus alpha square, which was the quadratic error in the parameter. Suppose you replace this quadratic error in the parameters by a Bregman divergence. What's the Bregman divergence is just when you do an expansion of a function, you have the first term, then you have the linear term, and then you have higher order terms. The higher order term, that's the Bregman divergence. You know, that's the difference between the function itself and its linear approximation of the right. Suppose you put the Bregman divergence instead of the quadratic term in the parameter error. Okay, so that's something more general. You can show that your algebra is exactly the same. So in other words, what you're going to have, instead of the P matrix that you had before with constant gain, what you're going to have is the Hessian of the function with respect to which you're computing this Bregman divergence. So if this Hessian inverse, if this Hessian is like something like a norm, then it's diagonal, right? The C is something like norm, so taking the inverse is zero problem, right? It's diagonal. And if you take L1, for instance, what is it going to do? It's going to implement sparsity. So in other words, out of the set of all parameters that get the task done, because remember, learning is done on a need-to-know basis. So if you have this big overparametrization, you're going to have lots of possible solutions. Out of all the possible solutions, it's going to pick the one that minimizes a particular norm, for instance, the L1 norm. Okay? So it's going to be the one that gives you the sparsest set of parameters, ideally L0, but the sparsest set of parameters. And you can pick other things, anthropic norms and so on. You have other results on this. Okay. So what does it say? It says in our problem where we have a vague idea of the physics, but we don't know which is the physics, you can use the sparsity to pick the right physics. You just put a few of them there, and it will find, not only it will get the task done, but in the process it will tell you that's the relevant model. Okay? And the complexity is exactly the same as the usual adaptive control prediction. The only difference is that the constant P matrix, which corresponded to the quadratic form, is replaced by this Hessian of the convex function that describes the Bregman divergence. All right. So it's implicit. It's implicit regularization. You know, you don't add a term. You just change the gain. It tends towards the right thing. Okay. So I'll probably skip the details, but you can, for instance, in a mechanical system, you could apply this directly to the Hamiltonian instead of applying it to the entire dynamics. It works faster. So we've done exactly this example with 1 over r cube. We've done also an example like this, where you have 4 chemicals, and you have no idea what the equations are. They happen to be this, but nobody tells you that. So you pick all the polynomials, all the monomials up to degree 3, and you let the system figure it out. And it does it extremely well. Right? So in other words, you have 4 chemicals, you have no way to know how you don't know how they interact, or you're too lazy to too lazy to figure out how they interact. You just throw monomials up there, you say, up to degree 3, let's say, or it could do 4, and it finds the right way to do either adaptive control or prediction. Okay, so 2 minutes to so transfer learning. Okay, so maybe I'll go quickly through that. Okay, but so basically there's a whole industry about computing contraction metrics and so on. Suppose you have an optimal policy, okay, expressed as a value of something minimizing the cost to go, right? The value function. Well, the cost to go is a Lyapunov-like function. So you can do exactly this. In other words, you can say, okay, so I have my nominal Lyapunov-like function that happens to be the cost to go, which indeed perhaps I've learned very painfully through hours of experiments and days, months of hours of computation or months of experiments. And now I can change the parameters, and I have one formula which is going to work immediately to get the same result. Okay, and so basically, I don't have time for this, but basically what it says the cost to go is a Lyapunov-like function, and therefore we know exactly how to do adaptation. We do adaptation exactly as we do adaptation exactly as we did before, where V0 now corresponds to this Lyapunov-like function corresponding. Right? Very, very simple idea. This more subtle point, and you can do implicit regularization the same way. The more subtle point, I won't have time to talk about it, is that it works also for unmatched uncertainty. In other words, if uncertainty doesn't appear directly in the dynamics at the right level. So I don't have time to talk about control instabilities, but we can talk about it if you're interested, or quorum sensing, or just the last point. About the same time we were developing contraction with Winnie Lomiller, some biologists at Berkeley and Harvard, Gerhardt and Kirschner, wrote this. Well, actually, this is later, but they started doing it at about the same time, the late 1990s. They had this notion of facilitated variation. The idea being that in biology, there are core processes like DNA replication or sexual replication, something like that, which took a lot of time to fine tune. Now you don't touch them anymore. What you do is what evolution targets is how you put them together. Okay, and that's exactly what happens in contraction, right? You have these contracting subblocks, and then you have all these rules to play these Lego axes. So just for fun, that's the coming Neurops who were surprised that it went right through. But anyway, just for fun, we applied this to RNNs, right? So we have RNNs like this, and we have conditions for these RNNs to be contracting in their individual metrics and so on. And we have conditions to be able to combine them in parallel in hierarchies that are easy, and also in feedback. This is the condition you have where these B's are arbitrary matrices. Okay, so the M's are the individual metrics of the system. This is how you connect the system, and the B's you learn. Right. So it's exactly doing facilitated variation, but with these contracting RNNs. And it turns out to work really well if you apply it to, for instance, we didn't have Google scale computation available at the time, but basically, if you do, for instance, permuted MNIST, you actually get state of the art on just doing that. So we've talked about stability, 2 forms of stability, both of which are inspired by virtual physics. We talked about the fact that if you apply this contraction to gradient descent, then you find exactly the topology, and you assume a system is semi-contracting in some metric, then you find exactly the topology of global minima that you find in standard, deep learning. We showed how to do adaptive prediction and model discovery. In other words, how to use implicit regularization to impose sparsity, which in turn can be used to choose between models. Okay. And we showed also how to do transfer learning. In other words, if you spend a lot of time learning something using whatever method you want, okay, how to now do very simply adaptation to structured parameter changes. So, stop here.